what is the objective here? The goal here is we want to use a pre-trained model like, for example, Hugging Face transformers, which is used for basic NLP tasks like sentiment analysis, or NER, which stands for entity recognition. Okay, we also want to analyze predictions and understand the limitations of such models like the Hugging Face transform model. So what we are going to do is we have some input text like this, and we predict the sentiment. And we also put a confidence score next to that sentiment. And we also want to find out the entities, like, for example, here, the person, the organization, and the location in the text. And we want to print it out in the text, like in these, like here in this example. Okay, just raise your hand or just put on your mic and tell me what's going on. So what are we going to do? We want to load a sentiment analysis pipeline. And for that, we load a model. For example, we use a model like BERT. BERT stands for bidirectional encoder representations from transformers. And then we observe the predictions made by that model by inputting some texts. Let me quickly show you a couple of available models on Hugging Face and how easy it is to use them. So if you go on Hugging Face, you don't even need an account, I think, to do that. And I go to this Dilbert models, then you can see there's a lot of models. Why are there so many of them? Because they are fine-tuned for specific use cases. What we are going to use, I think, it's the first one. You can also kind of guess how popular they are if you take a look at the number of downloads. So these two are probably the most popular. And I tell you the difference between those two in a minute. So we're going to use this. If you click on it, you also get a little bit of details about it, like as I said, how popular it is, how many parameters it has been trained on, and yeah, all kind of background information to this model, how it is used, some example code like here, and for what language it's optimized, stuff like that. But the way you're going to use it is just you need to copy the URL. That's all. Okay. Other than that, you don't need anything. It's completely open source. Okay. So yeah, we're going to use, let me copy that for a second. Just put it here. So let me quickly explain this name here. So uncased. Uncased means it ignores capitalization, which is good because then we don't have to do this in pre-processing if the model does it automatically. It's also fine-tuned, as you can see, and is fine-tuned on a specific data set. Data set is called SST2, and it's just a standard data set for binary sentiment classification, so positive or negative. And English, of course, means it's designed for English language text. But when you take a look back at the page, you will find a lot of other models trained for other languages as well. Good. Okay, so we start by importing the relevant libraries, and because we're gonna use transformers, we have to import transformers first. And what we're gonna use from transformers is pipeline, because we build a pipeline too, where we put the text in and the sentiment comes out, okay? And we also define our model. I save this in a variable called model, and yeah, that's just the URL that I have copied. And then I don't explain all the code right now in our introduction because we're gonna go into more detail in the specific types, in the specific parts of this code later. So but just bear with me, and I'll try to explain it in more detail when we come to a specific topic. For example, pipeline. So we build a sentiment analyzer. So I call it sentiment analyzer. And we use the just imported method pipeline. And in this pipeline, we use sentiment analysis. Then we have to tell which model we are using. We are using what we have just saved here in model. So that's the model we are using. And what you can also, but this is not a mandatory parameter, but because I'm on a MacBook Pro with an M3 chip, I can make use of that and tell them that it can use this GPU. So if you have a Mac with a M4 or M3 or M2, M1 chip, you can use this. If you don't, or if you have a GPU like an NVIDIA card, you can put in here device GPU. Other than that, you just leave it. You skip this parameter. I don't even think it's faster. Let's be honest. I don't think even, at least my MacBook is not really faster using that, but I'll just put it there anyway. And then we come up with some random text, okay? So let's start with just some random text where it's pretty clear what the sentiment is. Let's say I love this NLP course and I am so happy I have signed up for it! Exclamation mark. And all the other, all the other courses are so frustrating and difficult to understand. Let's leave it at this. Remind me that to be clear that the first one is positive, second one is negative. And now we just get the predictions by writing a simple loop over over this list here. So for text in text, that's our list. So we go over the list with this loop. And for each element in the list, we want to get the sentiment using our just initialized sentiment analyzer, and the sentiment analyzer needs these sentences. So we go through, you hand over the first sentence, we use the sentiment analyzer, and we save the result, which is the sentiment in result, and then we print out the result. Let's make it a little bit more readable by printing out the text as well, so that it's easier to put these two things together. Let's say, okay, here's the text, and here we have the text, and then in the next row we do, here's the prediction, call this result, and then let's also do a new line so that it's also more readable, because we are running through that list, and we also will add more sentences to it. Let's try that out. Okay, we get some future warning. If you get a future warning, it's not really serious. It just tells you that in some future time, some behavior will alter. So just be aware of that. Doesn't make any difference. So here, first sentence, we have a positive score, and the model is 99% sure about this score. And for the second, we have a negative score, and the model is also 99% sure. It isn't all that surprising, right? So these fine-tuned models are kind of biased. Or not only the fine-tuned models, a lot of models, or bias is always a problem with pre-trained models, because you don't know what they have been trained on. You might have heard that before. So let's quickly check. And this is always a good best practice, how biased the model is and where you could run into problems. So I'm giving you some examples, but maybe we can brainstorm some more examples together. So let's do something like this. Course was originally created in, let's do Afghanistan. Is that correct? Afghanistan. And then, just for comparison, let's do Italy. let's just see if the model thinks, because it shouldn't make any difference, right? Why should it be one positive and one be negative? So let's see what happens. Yeah, you should also put on a comma here. Otherwise it thinks it's still 2 elements. So now we should have 4 elements in this list. Yeah, it's a perfect example. Do you see that? It's 91% sure this sentence has a negative sentiment, and it's 90% sure this has a positive. And I just changed the country. That's not a little biased, that's heavy biased, okay? Let's try one more example. Let's do, what about this? This product, this manufactured in China. And because it has been working so well, let's do Italy again. Okay, let's see about that. You see, same thing. It's not so sure anymore, but it's still 61% sure. If it's manufactured in China, that's a bad sign. And it's 62% sure if it's manufactured in Italy, that's a positive sign. This business is owned by a Jewish entrepreneur. Entrepreneur. And too much. Entrepreneur. And let's do we do white? Oh, how do you want to test it? Yeah, for example, yeah, let's do white. Okay. Okay, that's not a problem. Interesting. Let's try. What about Hispanic? Okay, so you see, it's not biased on every aspect. Anybody else has an idea what we can test? If it's not ethnic background, maybe what about names? Because names are also specific to specific cultures or ethnics. What about that? Let's try our lead engineer. They developed this algorithm. Let's try that. And then we take another very typical name. Let's try a basic name like John. Oh, you see that? 74% negative. Huh. Because I would say Sade is maybe a typical, a name that is mostly common in Afro-American culture, I would guess. But you see the point, right? You see what I wanted to bring across with that. So these models are good, but take the results with a grain of salt, or at least be cautious what type of sentiments or what type of text you're feeding into this. Yeah, because when you take a look at this card, it says something like, yeah, they tested it with different data sets, and you get results like 91, 89, 93%, 97% accuracy. So all of these are good scores, but we have now 8 examples, and 4 of them are total BS. Yeah, so that's what I wanted to bring across. If it's a pre-trained model, test it really, okay, and not just with basic examples. Oh, okay. Good. Then let's get to the second point, which was named entity recognition. So again, we use a pre-trained model, and now we don't want to identify the sentiment, but we want to identify or extract entities like names, dates, organizations, locations, etc. Okay. So let's try person, location, organization, and maybe miscellaneous. Okay. Of course, we need to import again the libraries, but we already have imported transformers. And we don't have to do this again. It's just if you run it separately, I put it here again. And we use a different model now. However, I don't remember the exact name. So I'm going here. There are search models. It was something like this. Yeah, that's it. Yeah, so let's use this. It's called Bird Laughs. So it's a little bit bigger. How big is it? Okay, it's 334 parameters. So it's probably quite big. And it's fine-tuned for English again. So let's copy that and put it here. And again, we load the pipeline. Now it's not a sentiment pipeline, but it's an entities pipeline. So I save it or initialize it again with pipeline. And this time it's not sentiment, but it's named entity recognition. We want to group the entities. So we set this parameter to true. We have to tell again which model we want to use. And also, I'm going to use my M4 processor. Yes, okay. It's okay. Test. Now we need a new text. We need to come up with a text. Okay, let me think of something. Okay, how about the lecture is held by vice lecturer at ONI. So I'm trying to come up with something that checks all the boxes, so all the entities. And when you were certain and working at streaming banks born in Germany. Okay, so there are some entities in it. Now we need to extract them and save them. So we use our initialized names entity recognizer. We hand over our text, which I just defined. We don't need a loop because it's just one text. And again, we print out the results. And to make it more readable, I print out the text as well again. Text. Let's do a line break. And then we call it entities. And the entity for the entities, because we don't know how many entities are in it in this sentence. That's what we want to find out. So we need to loop over the results, which we have just saved in entities. and print them out. All right. Let's go quickly over the code again. Here's the name of the model. I just copied it. I initialized my pipeline using NER. I'm setting this parameter to true because I'm going to get the entities. I'm using this model. I'm using my M4 processor. That's the text. There's a lot of entities in it. And saving those in entities. And then I loop over entities and print out each entity. And you also get where exactly in the text you find this. So that's the number 23. Yeah, so that's the 23rd letter, and it ends at 36. So that's the 36th letter. Yeah, pretty easy, and it's pretty confident about the entities in this sentence. Again, please try to replicate that, because after that we move on to a little bit more complicated sentence, because now you know you should test these models with all different kinds of text, or like more complicated stuff, and not just take it for granted that it's working now at 99%. I'm already thinking of a sentence that is more complicated or that has some pitfall in it. Yeah, we usually just provide some more edge cases or just more difficult examples. And maybe we have to switch then the model if it's not working with this one. Or we have to try different parameters. So let's just copy paste this and try it out with a little bit more complex text. Okay. So let's try. You can also use your own text, okay? So you don't have to use mine. I'm just thinking of something more edgy. Let's try to write a typical German nested sentence with a lot of commas. Previously worked at a bank in Frankfurt. Before joining and family. I like to use brackets. Brackets always nice. And on the side, yes, academic duties in Colorado. Object and free being beats and Smith were not an end. And shall we guess in instrument or and the guard in Germany. Oh, Hey, that's a complicated one. Okay, that should be a challenge. That should be a challenge. Let's see how the model handles this. Yeah, not so well. So first problem. You call this problem token fragmentation because subwords like here, bo, tano, they haven't been split correctly. And another problem is here, like you call this entity overlap issues because it should it's one word. So transactions on AI, they belong together. So it's not transactions on and AI, but one word. So they overlap. And there's the rest is okay. That's good. And now that's not an entity at all. The rest is okay, I would say. But these 5 examples are problems. So yeah, try it out with your own sentence. Let's just try a different model, but with the same text to see if a model that is specialized in token fragmentation and also is good at entity overlap issues can handle this better. So let's first of all copy and paste it here, and then look for a model that is good. Gotha, Nord, NER, I think. Gotha Lounge, English? English? Is it that? It's not very popular, but I think I tried this one before and it has worked pretty well, but it's not popular. It just has 70 likes and only 161 downloads. But I mean, it doesn't hurt to try it out, right? Okay, so let's try that. Perfect. You see, no problems. It recognizes this now as an organization, and it also recognizes transactions on AI is the journal. Okay, also organization. Very good. Good model. Interesting that it's so not popular. Let's start with an introduction to text classification. Of course, we start with a definition, and text classification is simply the process of categorizing text into predefined labels. That's important. It's predefined labels. So, for example, spam detection or sentiment analysis that we have already seen now. And we differentiate different types of classification. Basically, you could say there are 3 different types. The first one is binary classification. So we have 2 classes. Again, something like spam or not spam. We have multi-class classification. That's more than 2 classes. For example, we could categorize different topics. And we have multi-label classification, meaning assigning multiple labels to the same text. So that's also possible. And a very classic example for classification is, of course, the mentioned sentiment analysis. So again, what is sentiment analysis? As the name suggests, we determine the sentiment, so positive, negative, but also neutral, which we haven't seen yet, which is expressed in the text. And there are basically 2 methods to do this. The first method is rule-based, and it uses predefined lexicons. with certain birds or blacklists. And the other one is, of course, machine learning. So trained models on labeled sentiment data sets. And one special form of this machine learning trained models is something called zero-shot classification. And we take a look at this now first. Zero-shot classification is a technique that allows text classification without training on specific labeled data sets by using those pre-trained data sets, for example, those Hugging Face transformer models. Because in this way, you can classify text into user-defined labels without additional training, without additional fine-tuning. Why you want to do that? Because it's expensive. First of all, that labeling of the data, if you have to do it yourself, is pretty time intensive, and that costs money. And then training of or fine-tuning of a model, that costs because you need compute power. So that's like the second best plan is using a pre-trained model with the aforementioned downsides. And I give you an example for that. So yeah, we have already seen this. We have input, like I love this product. We have labels like positive, negative, neutral, and we want to see an output like this: positive with a score, or neutral with a score, negative with a score. And of course, if you sum these three, they have to the sum has to be 100%. In Python, we have a lot of different libraries that help us to do this, so we don't have to reinvent the wheel. I've already mentioned Hugging Face transformers pipelines with models like the one we use with the distill.base on case models. And the problem is how we can now figure out how good is our model, how good is how good is the job done, or the job of classifying our inputs done by our pre-trained model. So that's where these evaluation metrics come into place. So let's take a look at what we got here. So there are 5 key metrics we use for evaluating classification, and they're called accuracy, precision, recall, and F1 score. And typically you display them in something that is called a confusion matrix. And to better understand them, I will go through this matrix and plot it, the positive and negatives in a matrix. So we have actual positives and negatives, as well as predictive positives and negatives. In all those positive cases, where the actual results and the predicted result match, that's what we call true positives, because they are true and they're positive. So those results where the predicted and actual value were negative, those we call true negative, because they're true and they're negatives. Results we predicted as positive, but who were actually negative? Might have guessed that's false negatives, false positives, sorry, because they're false and they're positive. And lastly, results that have predicted negative but were actual positive, that's false negatives, because they're false and then negative. Okay, let's try to understand this better using an example. So we have this graph here. Yeah, let's say all the circles are positive results, all the triangles are negative results. And our model predicted these results as positive and these as negative. So in that case, our true positives, so that's all the circles inside the green line, which are a total of 8, right? And all our false positives will be this one triangle inside the green line. So that's 1. Okay. Similarly, we can also calculate the false negatives, and we can also calculate the true negatives. All right. You also sum it up across predicted and actual results. And if you are confused, yeah, if you're already confused, that's probably where the name is coming from, because now we have calculated the confusion matrix. Just a small trick to not get confused with all those names is to separate the naming process. So 1, was the label true or was it false? And 2, was it positive or negative label? Because this way you're way faster to distinct between those 4. Sorry. So let's take a look at the different metrics we can now calculate with these numbers. And we start with the accuracy. The accuracy is nothing but the proper proportions of total number of correct results. So the sum of the green numbers, so that's the true positive, true negatives, divided by the number of total observations. So we have, in this case, 8 true positives plus 4 true negatives divided by 15. Hence, accuracy will be 80% here, right? Good. Next one is precision. Precision is the proportion of correct positive results out of all the predicted positive results. So there is nothing but the true positives divided by all the predicted positives. We have predicted 8 true positives and total predicted positive results are 9. So it's 8 divided by 9, and that's 88.9%. That's our precision here. Up next, the recall. The recall is the proportion of actual positive cases that the model has predicted correctly. So here, the true positives divided by the total actual positives. In this case, we have a total of 10 results as positive, but we could only predict 8 correct and 2 as false. Hence, in this case, the recall is 8 divided by 10, and that is 80%. Okay? Good. Last one we want to take a look at is the F1 score. Well, the F1 score is the weighted average, or you also call it harmonic mean of precision and recall. When measuring how well you are doing, it's often useful to have just a single number to describe your performance. And this single number is the F1 score. It is basically the harmonic, not the arithmetic mean of precision and recall. And in our example, that's the formula, it would be 84%. I know, I don't know if you have already heard this. If you hear it for the first time, could be that these numbers can be a little bit confusing, but we will work with this a lot. So I give you just some example to explain it a little better. So let's say you want to detect fraudulent credit card transactions. That's at least that's where I'm coming from. So I'm using examples from financial. And a software company promises you that they have trained a model, a pre-trained model, that does just that with an accuracy of 99%. Accuracy is 99%. So by now you should already know this is a red flag, because we already know that is kind of nonsense, as the model might not predict a single fraudulent transactions, but be 99% accurate anyway. But what about recall? A high recall would tell us the model finds a good amount of the fraudulent transactions made. But this usually comes at the expense of a third metric, namely precision, because if you really want to make sure you don't miss any single fraudulent transaction, you will produce a lot of false positives. And what does that mean? It means your precision will go down. Okay, what's the solution? What do we do right now? We know accuracy won't be any helpful in this case. We know we want a high recall, but we also know we want a high precision. However, we also know there's a trade-off between those two. So in most cases, or in this use case of a bank wants to find a good balance between those two. A good recall, so that the regulators like above are satisfied, but also a good precision, so that the employees don't get overwhelmed. And a metric to help you with that is the F1 score, because it gives equal weight to both the recall and the precision, and it also punishes extreme values. Okay, so that's just one example how you would handle those different metrics. I hope it helps a little bit to understand these numbers. So, but before we move on, I want to give you also a practical use case on your own. And I want to show you an example on how to interpret these results when they come back to you, because that is really important to drive this point home. So let's just imagine a hypothetical scenario where you're the CEO of a company that is selling, let's say, subscriptions. Every customer that unsubscribes from your service will cost you 100 euro. So, of course, you go to your marketing team to create a campaign involving an incentive of, let's say, 10 euro. to prevent people from unsubscribing. As you don't want to spend €10 on every of your customers, you ask your data scientists, for example, to come up with a model that predicts which customer will unsubscribe from your service. And they come back to you with this matrix. So if you do the numbers, the accuracy, remember accuracy, proportion of total number of correct results of this model is 77%. Precision and recall are even worse at 47 and 40%. Okay, so what are we going to do now? I mean, you probably thought machine learning is this magic thing that can accurately predict anything, right? But 77% doesn't sound too promising, does it? But let's think about it. Are the numbers really that bad? Is the model really that bad? Let's just play it through one more time. Let's say we do nothing. If we do nothing, no model, no incentive, we will lose €2,200, right? You see that? Because if you use our model and only give an incentive to 19 people that it predicted to unsubscribe, that will cost us €1,490. Yeah, 100. Yeah, €19 for the incentives and 1,300 for the customers the model didn't predict. Meaning the model just saves us €810. Actually, the model only costs us more money than doing nothing if nobody or just one of the customers takes the incentive, because that would cost us a total of 2,290. Again, 190 for the incentives and 2,100 for the unsubscribers, meaning we would lose €90 in the process. Okay, but only in that case. So, and that would be a really, really bad marketing campaign if really none will stay on board. Okay, I hope that makes it a little clearer, right? It's important not just to look at the numbers, but it's also important to look at the business case in this scenario at hand to decide whether these numbers are good or these numbers are bad. There's no threshold where you say, okay, over this threshold, that's a good accuracy, or under this threshold, the precision is too bad for us to continue. Okay, it's floating, right?